Well, a warm welcome to anyone joining. Thank you for being here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, we're going to explore differential equations a little bit. It's what you would have seen in a calculus course when you're covering integrals and antiderivatives. We're going to use some applications of physics, specifically the kinematic chain, in order to understand the relationship between a function and its antiderivative, which is tied together through this integral. So just a little recap about kinematics. If you haven't seen this in physics already, you've seen this in calculus, that's for sure. There's a connection between the position of an object that's moving and its velocity and its acceleration. And that connection, if we go sort of up the chain or up the ladder, is a derivative. So we take a derivative with respect to time. And so we can think of the acceleration as the derivative of the velocity, and we can think of the velocity as the derivative of the position. Now, if we wanted to sort of go back down this chain, we would have to take an integral with respect to time, because we would be keeping track of changes in velocity or changes in acceleration over time. Remember that a change in acceleration, dv dt, if we multiply this by a certain interval of time, we end up with dv, which is just the change in the velocity. We can call it, let's just call it vf minus vi. That's the final minus the initial. It's the overall change. So an integral really is used here in order to keep track of the overall change and take us down the kinematic chain from acceleration to velocity and then from velocity to position. So we're going to solve some differential equations. As an example, you're going to have to do some more advanced applications of understanding velocity and speed and acceleration to answer other types of word problems in the derivative section, such as when an object is speeding up or slowing down, things like that, or what the velocity is at a certain time. But here we're going to focus on using the antiderivative process to solve some basic differential equations. So take a gander, take a look at the three differential equations that we have here. I didn't write it in a differential equation. That's up to you to do. Give these a shot, pause the video, maybe take about, 5 or so minutes for each one. So let's say 15 minutes. And then when you're ready, go ahead and unpause the video, come back, see how we did it. If you hear me munching, it's because I have watermelon next to me. Okay, let's get started here. We have a bottle rocket that is shot upwards from a 20-foot stand, that's going to be important, with a velocity. Here's the equation for the velocity. What is the position of the rocket at t equals 2? So we're asked about the position, x of 2, and we're given the velocity. We're definitely going to have to use an integral in some way to get us to x of 2. So what can we do here? Well, first we can realize that velocity is dx dt, so that when we take an integral of it, I didn't mean to put this so close. When we take an integral of the velocity, we are quite literally going to end up with the position, because dx dt times dt turns into dx. So here we have x of b minus x of a. That's with an integral from a to b. What is our integral expression going to be, our integrand? It's going to be just the velocity expression. And what are our limits here? Well, here's where we need to use the given information to pick a really good value for one of the limits. Of course, we want to know what x of 2 is, so I think it's pretty obvious that we want one of these to be 2. Which one do we want to be 2? Well, kind of depends on what our given information is. It was shot upward with this velocity, right? But we also have this initial position because it was shot upward from this point. So we know that x of 0 equals 20. That's the height of the object when no time has passed by. So we should probably use limits of integration that involve 0 and 2, because those are the 2 points of time that we have some reference about. So we're going to basically use the integral of 40 minus 1.2t, and we're going to go from 0 to 2 dt, of course. Now here's a basic application of the antiderivative. You reverse the power rule of derivatives, so I'm going to put a t on it, and I'm going to raise the exponent on the t by 1 and divide by the new exponent. Take your time at first. You don't have to do it as quickly as I'm doing it. Take your time. So plug in 2. Let's see what we get. We get 40 times 2 minus, let's simplify that. It's just 0.6. So 0.6 times 2 squared minus what we get when we plug in 0. Fortunately, all that stuff's just going to turn into 0. So this is going to give us 80 minus 4 times 0.6. That's 2.4 for a whopping total of 77.6. Now, what is this integral expression equals to? It's equals to x of 2 minus x of 0. So we are not done here, ladies and gentlemen. This is not our final answer for the position at 2. We have to replace, we're going to add x of 0 on both sides. We have to replace x of 0. That's our initial condition. That's why we picked 0 as a time, because we know some information about the position at 0. It's 20. So the integral tells us what? The integral tells us how much the position has changed. This is still a very useful number. This is the net change in the position. This is how much the position has changed from time 0 to time 2. But that's not the final position. That's just how much it's changed. If we didn't start on the ground, then we're not just 77.6 feet in the air, for example. I forgot, is this feet? Yeah, 20-foot stand. So I guess everything we just assume is in feet. That's going to give us 97.6. That is the position x2, the position at time 2. Okay, great. Let's take a look at problem 2. That was easy. That was number 1. That was just like a warm-up problem. Number 2 is a little more involved because we start with the acceleration. Oh, and I'm sorry if you solved these problems without the exponent on them. This should have a 2 and this should have a 2. So if you already solved them without that exponent, go ahead and just solve the new ones again. You can take the time to do that. Or you can just wait and see how I did this one. I won't, unfortunately, be checking or providing a solution for how it would be done without the exponent, so we're just going to have to accept that I forgot to put that before I encouraged you to pause the video. Alright, let's get started. We have the acceleration at time t, and it's a quadratic expression. We have an initial velocity. Initial means what? This means time t equals 0. So they're basically telling us that v0 equals 3. Okay. And they're also giving us an initial position at 8, which means that at time t equals 0, basically v0 equals, x0 equals 8. You can use x or you can use s. Sometimes you'll see s being used. Doesn't really matter, just pick one. And the goal of the problem is to determine the function for the position. So we're looking for x of t. Well, we're going to have to use this kinematic chain idea. If we're starting at the acceleration this time, we need to take an integral to get to the velocity, and then we need to take another integral to get to the position. So let's get started with that. Remember that a is the same as dv dt. and this was 3t squared plus 4t plus 6, is that right? Yeah. We're given the initial condition that v0 equals 3. Let's go ahead and use the fundamental theorem of calculus here to say that the integral of at dt, basically just the integral of dv dt and then times dt, right? This is going to give us our change in v, which is going to give us v of, let's call it b for now, minus v of a. We need to pick our limits of integration here. Well, we're given the initial value here of 0, and we need to find the expression for v of t. So our second value is going to be t. So let's set this up on an integral. This is the integral from 0 to t of 3t squared plus 4t plus 6 dt. And then we're going to say that's equal to v of t minus v of 0, which we know. So we'll be able to use this to our advantage. But for now, let's worry about the antiderivative portion on the left side of the equation. So raise the power by 1 and then divide by the new power. It's the most simple rule. The best way to get good at it is to say it out loud every single time until it's literally second nature. Okay, that's just the best way to do it. So this is going to be evaluated from 0 to t, which is kind of easy to do, right? Because if I plug in a t, I just get the expression. I'm going to simplify the fractions, right? I can simplify this fraction, and I can simplify this fraction. But other than that, I'm just replacing t with t, so therefore nothing changes. And then we subtract what we get when we plug in the lower limit of 0, and it's no surprise that I just get 0 plus 0 plus 0. So really, all I have is t cubed plus 2t squared plus 6t. And this is equals to, let's use the right side of the equation now. This is equals to v of t minus 3. Last step, of course, is to just add 3 on both sides. And now we do have an expression for the velocity, which is useful. However, the goal of this problem is to find an expression or a function for the position. So we're going to have to go one more step down the kinematic chain, go down to position, also using the initial condition. So the initial condition here, remembering that v is just dx dt, with the initial condition, right? We always want to think about this as sort of like it came from the derivative of something. V of t came out of the derivative of position. And then we use an initial condition for the position. Oftentimes it helps. So let's use the same principle. I'm not going to write out all the nitty-gritty details like v of t, dx dt, dx. I'm not going to write it out like that. That's just from the fundamental theorem of calculus. You should know this. But we are going to discuss what values of t we want for our limits. Of course, we want 0 as one of them. X of b minus x of a. That's from the fundamental theorem of calculus. We want one of them to be 0, and we're just going to say that b equals t. Okay? So, let's go from 0 to t on the velocity, which is equivalent to doing the integral from 0 to t of this rather large function, right? T cubed plus 2t squared plus 6t plus 3. Right, that's no short expression. And we're going to have to take an antiderivative. So raise the power and divide by the new power. Raise the power, divide by the new power. Just say it out loud like it's a mantra. Raise the power by 1 from 1 to 2, divide by the new power. Slap a t on the 3, and we're going to evaluate this one from, again, some pretty easy values from 0 to t, so it should be no problem at all. We're just going to simplify one of those terms. We're going to simplify the third term because 6 over 2 is just 3. So we have 2t cubed over 3 plus 3t squared plus 3t minus, what do we get when we plug in 0? Yeah, 0 plus 0 plus 0 plus 0. Not very interesting there, sir. But now we can use our right side of the equation for the fundamental theorem. 1/4 t4, 2/3 t cubed, 3t squared, 3t equals minus 8. So now all I have to do is a little algebra, add the 8 plus 8 equals x of t. And now this position function can tell you the position at any time. If we just use the method we did last time in the first problem, which was to directly use 2 and 0, we get a specific value. We don't get an expression that can be used for other time. Okay, let's go to the third and final problem. This bit of information tells me that v of 3 is equals to 10, and this bit of information tells me that x of 1 is equal to 4. So I'm going to use these two conditions. Okay, let's start off with the fact that acceleration is dv dt. It equals 6t squared minus 2 with the initial condition that v of 3 equals 10. The initial condition, or the condition, doesn't have to be at the moment 0, by the way. I know the initial generally does mean 0, but we just need some starting moment reference. It's kind of what we mean by initial. It's like the first point in time that we have any information about, not necessarily time equals 0. Okay, anyways, let's get to the integral of the acceleration. And we're going to use t and 3. Why am I using t here? Well, I don't want to know the velocity at a specific time. The goal of this is to find the position at a specific time. But the velocity, I just want a velocity function. So I'm going to use a limit as t. And this, of course, is going to give me v of t minus v of 3, which we know for the expression 6t squared. And we're going to just raise the power by 1, divide by the new power. Very straightforward. And then for the 2, you just slap a t on it. You can literally slap it if you want. And we're going to evaluate this from 3 to t. Now when we plug in t, of course we just replace that. Let's simplify this to 2. So we're going to have 2t cubed minus 2t. But then we have to subtract what we get when we plug in 3. So this is going to be 2 times 3 cubed minus 2 times 3. Which gives us 2t cubed minus 2t minus, what is all this jumbo? 2 times 27 minus 6, or minus 2 times 3, which means we have a total of just 48. So there's our expression. What is this equals to on the right-hand side using our fundamental theorem of calculus? If I'm making you dizzy, I do apologize. Now we need to solve for t, so we're going to add 10 on both sides. And we get an expression for the velocity, which is 2t cubed minus 2t minus 38. Okay, we do not need the velocity to solve this problem. We need the position at a specific time. Remember that the velocity is the derivative of position with respect to time, dx dt. And we have the initial condition or starting condition for the position. Use time equals 1. And we want to know x of 3. So that's going to determine our other limit of integration. So we're going to go from 1 to 3 of the velocity. And that's going to give us x of 3 minus x of 1. And then we can simply move the x of 1 on the other side. For now, let's worry about the left side. We need to do another integral, another antiderivative. And the expression here is a bit longer. 2t cubed minus 2t minus 38 dt. Well, that's going to raise the power by 1, divide by the new power 4. Raise the power by 1, so it's a 2, divide by the new power 2, minus 38, and just slap a t on it. And we want to go from 1 to 3. These are fairly easy numbers to plug in, so you're expected to be able to do that comfortably. Let's see, this is like 1/2, and this just cancels the 2's, so we're going to have 3 to the 4th over 2 minus 3 squared minus 38 times 3. Oh, come on, you guys are in good shape for that, right? Minus 1 to the 4th over 2. 1 to the 4th is kind of redundant, but it's okay. Minus 1 squared, also kind of redundant. Minus 38, I'm not going to put times 1 because it's just 38. So let's see what happens here. We're going to have 81 over 2 minus 9 minus 38 times 3. You'll see why I'm leaving it like that for now. Then we're going to have minus 1 over 2 and minus negative 1, so like plus 1. And then minus negative 38, so plus 38. Why is it useful to do this? Because these terms usually match up. If they're fractions, it's going to be convenient to work with them together because that makes a whole number, 40. Negative 9 and positive 1, that makes a negative 8. And then here we go, we have negative 38 times 3 and positive 38. That's the same as negative 38 times 2. Hopefully you followed that. This is simply going to be, it's just easier to multiply 2, isn't it? This is going to be 32 minus 76, negative 44. Now this is just the left side of the equation. That's just this part here. We still need to bring this all down from the fundamental theorem of calculus on the right side of the equation. So this is equals to x of 3, which we're interested in knowing, minus x of 1, which is given as an initial condition. So here we say negative 44 equals x of 3 minus, what position did I give this? I think it was a 4? Yeah, 4. Minus 4, which means the position at x of 3 is negative 40. And that's okay to have a negative position. That just means you're backwards. You're sort of facing backwards from what we would consider positive. This gives us the final position. All right, so this is how the kinematic chain allows us to set up a differential equation and then solve it using the fundamental theorem of calculus and antiderivatives or integrals, like your bread and butter. So I'll see you guys next time.